Let's take a look at our homework question number 2 from page 492 from over the weekend. Number 2 says a 100-kilogram hockey center is moving at 1.5 meters per second to the west in front of the net. He is checked by a 108-kilogram defenseman skating at 4.2 meters per second to the south. Both players move off together after the collision. What's the velocity of the center of mass of the combination of the two players? Remember we talked about center of mass on Friday, how really the mass is kind of spread out over a bit of an area, but we can consider it to be in one place. Okay, that's what we're looking for here. They stick together. That one point where the center of mass is, where does it go? All right, let's draw a picture here because that's helpful to us here. All the questions? Yep. That's helpful to us here. We have a 100-kilogram hockey center moving at 1.5 meters per second to the west. We'll call that object number 1. He's going to the west, 1.50 meters per second, and his mass is 100 kilograms. Listen, it's always okay to draw a diagram, but it's almost essential to draw a diagram when you've got a two-dimensional problem like this. Draw the picture. You got to write down givens anyways, so you might as well draw the picture and write down your givens that way as just to list them. We've got a 108-kilogram defenseman going south. We're going to call that object number 2. His mass, 108 kilograms. His velocity, 4.20 meters per second. They stick together and head off as one. Which way do you think they're going to go? Yeah. The resultant vector, yeah. What's your prediction, though, as to roughly what direction that would be? I don't expect you to give me an angle right now, but Rosie? Yeah. That way, down and to the left. Why down and to the left? Well, if we have momentum before the collision to the left, we have to have momentum after the collision to the left. If we have momentum downwards before, we have to have momentum downwards after. So it's going to go down and to the left. Now let's figure out what that is. We do that by breaking it up into x components and y components. For x, we would say pi equals pf. We would say m1 v1I plus 0. Why 0? Good. If we're analyzing the x-axis, this one is not moving on the x-axis. It's moving, but only on the y-axis. So we're going to consider that to be 0, as if the object wasn't even there. Afterwards, they stick together, and they're both moving on the x-axis afterwards, so we include both masses there. M1 is 1.5. V1I is negative. No, sorry, M1 is 100. V1I is negative 1.50. The combined mass is 208. And VF is, we'll find it here. What does that work out to be? 150 divided by 208? Somewhere around 0.7 something? 0.72, 0.73? That's going to be negative though, isn't it? Meaning it's to the left, which is exactly what we predicted. Rosie said the final momentum is down and to the left. Sure enough, the momentum is the velocity, and therefore the momentum is to the left. Now let's do the y component. And we'll see what the y component of the final velocity is. We say pi equals pf. We'll say it's the momentum of object number 1. For the y component. Chase, what's the y component of number 1? Yeah, how much of that 1.5 meters per second is up and down? 0, none. Right? It's all horizontal. So we're going to say the initial y component of the first one is 0. The y component of the second one is m2 v2I. Equals, they stick together, so it's MVF. So we're going to say M2, what is it, 108 kilograms times V2I, which is negative 4.2, equals 208, the combined mass, times VF. That's what we're looking for here. Do the math there, we get negative 2.18. Meters per second. All right, so now we got the x component of the final velocity and the y component. So let's combine them, right? X is 0.72. Y is 2.18. We can drop the signs now. The arrows tell us the direction now, right? The only reason we had the signs in here was to tell us what direction it was. Now we're drawing arrows to show the direction. My resultant is going to go right here. I'm going to say V is equal to the square root of 0.72 squared plus 2.18 squared. I assume for that we get the answer that's in the book, 2.30. And theta is the inverse tan function of opposite over adjacent. And I assume for that we get 71.7 degrees south of west. Yeah, is that what we end up getting? If you had have drawn this slightly differently, we could have drawn it like this. What would you have gotten for V there? 2.3. What would you have gotten for theta? 28.3? No, 18.3? But it would be 18.3 degrees west of south, right? All right, if that's okay, let's try another one. We have a 0.6 kilogram fireworks bundle that's at rest just before it explodes. Listen, I've been telling you since we started conservation momentum that we use it whenever we have a collision or an explosion. But I said it doesn't have to be literally an explosion. It can be literally something like throwing a ball. Well, finally, we have literally an explosion. We're going to use conservation momentum here, but it's going to be two-dimensional conservation momentum here, X and Y components, because it's not all on one axis. Some of it's this way, some of it's this way. Okay, we cannot do momentum because momentum is a vector. We can't do it just pi equals pf if there's two axes involved. This fireworks bundle explodes, let's say at this point, point X. We get a 0.20 kilogram fragment going to the west. I'm going to call that piece 1. 0.20 kilograms at a velocity of 14.6 meters per second. We get another one going to the south. We'll call that fragment number 2 with a mass of 0.18 kilograms and a velocity of 19.2. There's a third piece. There's a third piece. Where is it going to go? Where do you think it's going to go? What was the initial momentum of this fireworks bundle before it exploded? Easy answer. Devin? 0. Good. What is the final momentum of this fireworks bundle after it explodes? Again, easy answer. Eve? 0, right? If it's 0 before, it's 0 after. Sometimes we get an answer that's so easy. Sometimes we're like, no, it can't be. Right? Like, I do that too. So it's like, no, it can't. So we have 0 momentum before, 0 momentum after. If there is a momentum to the left after, then there has to be a momentum to the right to cancel that, right? To give me a 0x momentum. If there's a momentum downwards after, then there has to be a momentum. A momentum upwards, right? So if we have down and left, we have to have, for the other piece, the third piece, up and right. Does that make sense? The up counters the down, the right counters the left. Holly? Oh yeah, thank you. No, that's okay. Thank you. All right. We know what to do here now, right? X components, Y components, PI equals PF. Hey, what's the initial momentum? 0. You know, if this fireworks bundle was moving when it exploded, then we would say the initial momentum was MVI. One object before it explodes times VI. But it's not moving, so let's just say it's zero initial momentum. But afterwards, now we have three objects for the first time. M1 V1F plus M2 V2F plus M3 V3F. Now, I would love it if all the masses were the same, because if they were, that would allow me to do what? Cancel them. But they're not. You got to deal with it. M1 is 0.20 kilograms. V1F, negative 14.6. M2, it's 0.18 kilograms. What's V2F? What's V2F there? Brendan, you got that one? V2F? Oh, but it isn't 19.2 meters per second. Not right now, it isn't at least. It's zero, good. Because we're dealing with the x-axis, right? It's 19.2 on the y-axis. It's zero on the x-axis. Oh, what's M3? You don't tell me what that is. Yep. How'd you get 0.22, Yumika? Excellent. Yep, perfect. Take the total mass and then subtract the other two from it. 0.6 minus 0.2 minus 0.18 gives me 0.22. So we solve for V3F there. 2727 or 277? Okay. Thank you. You get a 13.2727. Oh, wait a second. Something's up here. Yeah, it should be positive. Hey, but you know what? I'm glad you said that. I'm glad you said negative. How did I catch that? Okay, how did I catch that? Wait a second, it shouldn't be negative. Yeah, we know that it's going to the right for sure. We know it should be positive. Now, the good news is it was only a sign mistake as opposed to some other mistake. Just be aware, right? Be aware. Christian? For the initial, for the final, you mean? Yeah. So V1F is negative 14.6. Okay. And V2F, we just said was zero, right? And the reason we said V2F was zero, even though it's really 19.2, is because we're dealing with x-axis right now, and that's only on the y-axis. Christian, when we get to the y-axis in 30 seconds, you're going to see that V2F is negative 19, right? Because it's going downwards. Okay, so let's deal with the y-axis now. Pi equals Pf. Christian, what is the initial momentum on the y-axis? The initial, as this fireworks bundle is sitting on a desk somewhere. Right. Yeah, because it's sitting there. Good. We have three objects. Actually, I say we have three objects, but really, we can get rid of one of them. Maddie, which one can we get rid of here? Number one, how come? Good. We're dealing with the y-axis, and it's on the x-axis. We could have avoided even writing down that term if we wanted to, right? 0 is equal to M2, which is 0.18. Christian, what's V2F here? Good, negative 19.2 meters per second. And my mass 3 is still 0.22. Devlin, 15.709, just saying? Okay, and that's positive. Mathematically, it's positive, but we look at this picture and it's, yeah, it should be positive, right? Because it's going up. Thank you. 13 and 15. So let's redraw this now. V is the square root of 13 squared plus 15 squared. Theta is the inverse tan of 15 over 13. Let's say this half of the room is going to calculate theta. You guys are going to calculate theta. And then you guys on this side of the room and over are going to calculate V. 20.56, thank you, which we're going to round to 21, I think, right? You guys have the value of theta there? Chase, you got that one? 49.81, so 50 degrees. And that would be north of east, right? How do I know? Listen, I was wondering when these guys were going to calculate their angles on this side of the room. I was wondering if they were going to calculate the right opposite side and adjacent side, because sometimes you get mixed up with that, right? Opposite is 15, adjacent is 13. How do I know right now that Chase used the right opposite and adjacent side? What kind of angle should I expect to see if he did it backwards? Smaller one, right? If this is bigger than 13, then the angle has to be above 45 degrees, right? If it's smaller than 13, it has to be below 45 degrees. So I know he's done this right. 50 degrees north of east, or you could have went 40 degrees east of north. Would have worked as well. Got it? What's different about this question than the ones we did on Friday and earlier today? Yeah, yes, good point. There's 3 objects, sure. What else is different? It's a little bit more work, yeah. Because there's 3 objects and 2 dimensions, yeah. It's exploding, so the initial momentum is 0, yeah. Absolutely. Okay, a few little, those are all small differences though, right? In the end, like, it's the same thing really, isn't it? Like, so you're a framer, you frame houses, and somebody gives you the plans to a house, and this house has 3 bedrooms, and you frame the house. This house has 4 bedrooms, and you frame the house. Really, if you know how to frame a house, you know how to frame a house, right? It doesn't matter whether it's 3 bedrooms or 4 bedrooms, right? If you know how to do it, you know how to do it. Okay, this is really the same thing. Okay, framing is framing. Solving these problems, even though it's an explosion, even though there's 3 objects, it's the same thing as we just did a few minutes ago, isn't it? Really? A couple small little differences. Take a look at these questions on 495 and see if you can figure those ones out.